The trigonometric functions, sine, cosine, tangent, and the rest are functions that take an angle as an input and give a number out. When that angle is an acute angle, then the ratio that they give out is the ratio of a couple of sides of a right triangle with that angle as one of the acute angles. Sine of an angle theta is the length of an opposite side over the length of the hypotenuse for a right triangle that has theta as one of its small angles. What we want to do often is go the other way. We want to say, what angle gives me a sine value of such and such a number? Now, we've already looked some at this. We've had lots of problems where we got down to the point where we need to solve sine of theta equals 1/2, and we've talked about solutions to this equation. And when we go and do this, we are asking the question, all right, what angles have a sine value of 1/2? What we want to do now is to make that process more precise, and we want to introduce functions that go in the opposite direction, that will take a number, a ratio as an input, and give an angle back as the output. These are called the inverse trigonometric functions. Before we define them, let's remember the definition of an inverse function in general and some of their more important properties. So, recall that if f is a function, it has an inverse if it is 1-to-1. And what that means is that every output of the function f has only one input that goes with it. Graphically, we can say that this function is 1-to-1 if and only if it passes the horizontal line test. In this case, there exists an inverse function which we write this way, f with a superscript -1, such that a few properties hold. So I'm going to enumerate these properties here. Property 1 says that y is equal to f inverse of x if and only if x is equal to f of y, not f inverse of y, where x is in the domain of f, or f inverse, and y is in the domain of f. So, in other words, the inverse function and the function exactly switch the role of the inputs and outputs. If f takes y to x, if f of y is equal to x, that's exactly the same thing as saying that if f inverse of x is equal to y. They're simply exchanging what is the input and what is the output for every point in the function f. The domain of f inverse is equal to the range of f. The range of f inverse is equal to the domain of f. And this is again just because the inverse function switches the roles of the inputs and outputs. The domain of a function is the set of all possible inputs, and so the domain of the inverse is the same as the range of the original, because the inputs to f inverse are the outputs of f. Number 4, we have this property that we use often to check whether two functions are inverses of each other. We have that f of f inverse of x is equal to x for every x in the domain of f inverse, which remember is the same as the range of f. And we have that f inverse of f of x equals x for every x in the domain of f. Actually, let me write that with y's. Let me stay consistent with how I was writing it before. Number 6, the point A comma B is on the graph of f if and only if the point B comma A is on the graph of f inverse. And this is really just restating property 1, because the point AB is on the graph of f if and only if f of A equals B, which happens if and only if f inverse of B equals A, but that's exactly the same as saying that the point B comma A is on the graph of f inverse. One way of interpreting a property 6 is property 7, is that the graph of f inverse is the reflection of the graph of f across the line y equals x. So these are functions that we often look at in the abstract in algebra, and there are lots of functions that we look at that are very important. Lots of inverse functions we look at that are very important. So for instance, the function, the exponential functions and the logarithmic functions are inverses of one another that we work with. Now, when we ask what are the inverse functions to the trigonometric functions, we're going to run into a problem. And the problem is that the trigonometric functions are not one-to-one. So let's see what the problem is and how we can fix it. So let's take just sine, for example. The function f of x equals sine x is not one-to-one. For instance, we have that f of pi over 6 is sine of pi over 6, which is a half, but we also have that f of 5 pi over 6 is equal to sine of 5 pi over 6, which is 1/2. So this means that if I ask you, what is the angle whose sine is 1/2, well, we know that there's not just one answer. In fact, we know there are infinitely many answers. We've looked at this before. There are at least 2 families, or exactly 2 families actually, of solutions to that equation. 2 different infinite families of answers to that question. So that means that the sine function itself does not have a true inverse in the sense of the inverse functions that we know from algebra. However, we're going to be able to define a function which we are going to refer to as the inverse sine function, which shares some of the properties, shares the essential properties that we want. And the way that we're going to see how we're going to fix this is by thinking back on the graph of sine. So remember that the graph of sine looks something like this. We've got to label our relevant marks on the axis. And we know that sine starts at the origin and then heads up and gets to the point pi over 2 comma 1, comes down to pi, comes down here to 3 pi over 2, and then, comes down to 3 pi over 2, and then comes up to 2 pi. And continues on, of course, but I'm going to leave that there. And just from this graph, we can see why we don't have an inverse. If we try to use horizontal lines, we see that this graph does not pass the horizontal line test. I can draw a horizontal line which intersects the graph many times. And all we need for it to fail the horizontal line test is for a horizontal line to intersect the graph more than once. So this function, the sine function, is not one-to-one. However, if I restrict the domain of the function and I only look at a certain portion of the graph of this function, I do in fact get a one-to-one function. So what we do when we're going to define the inverse trigonometric functions, and we're going to do the same thing for cosine and tangent as well, is we're going to restrict the domain that we consider to get a portion of the graph which still has the same range as the original. We still want to cover all the possible outputs from -1 up to 1, but that passes the horizontal line test, that is one-to-one. So the way that we're going to do that with sine is we're going to basically ignore everything on the graph that happens to the left of -π/2. And we're going to ignore everything that happens on the graph to the right of π/2. And we're going to restrict our attention to the function sine, but only with the domain of -π/2 to π/2. So we could say that this right here is the graph of sine x with x restricted to -π/2 to π/2, which is one-to-one. So in fact, this is the function that we're going to take the inverse of. The inverse sine function is not going to be the functional inverse of the whole sine function. It's going to be the inverse of this restricted sine function. So let's see how we define the inverse sine function. The inverse sine function is denoted by this symbol, sine with a superscript -1. So we read that as inverse sine, is defined by y equals the inverse sine of x if and only if sine of y equals x, but only for restricted values of x and y. Only for x values between -1 and 1, and this is the important one, y values between -π/2 and π/2. So, the way to think about this intuitively, the inverse sine of x is the angle in the interval -π/2 to π/2, or is the angle y in -π/2 to π/2, such that sine of y equals x. So let's see a couple of quick examples. Let's look at inverse sine of 1/2. Now, we know that there are lots of angles that have a sine value of 1/2, but only one of them lies in the interval from negative pi over 2 to pi over 2. And we know that's always going to be the case. There's only ever going to be one answer to this question within the interval from negative pi over 2 to pi over 2. So inverse sine of 1/2 is pi over 6. And this is since sine of pi over 6 equals 1/2, and essentially pi over 6 lies between negative pi over 2 and pi over 2. Now, one way of thinking about it, a very, very good way, is to remember that the inverse sine function only gives results in quadrant 1 and quadrant 4. Furthermore, the results in quadrant 4 that it gives are always expressed using the negative angle, the form of the angle which is minus some number between 0 and pi over 2. All right, so let's see another one. What's inverse sine of 1? This is going to be the angle within quadrant 1 or 4 or their boundaries where sine takes a value of 1. Remember that sine is the y value on the points on the unit circle, and we know that the point right at the top of the unit circle has coordinates 0, 1. Furthermore, that point corresponds to an angle of pi over 2. So inverse sine of 1 is pi over 2, and for the same reason, since sine of pi over 2 is equal to 1, and pi over 2 is between negative pi over 2 and pi over 2. What about inverse sine of 2? Inverse sine of 2 is undefined, and the reason for that is that there are no angles between negative pi over 2 and pi over 2 where sine takes the value 2. Remember, we have these relationships between the original function and its inverse. The range of sine is the domain of inverse sine. The range of sine is from negative 1 to 1. That's the maximum and minimum value that the original sine function takes. Therefore, the domain of the inverse sine function is negative 1 to 1, and we have that spelled out here in the definition. And so, if I try plugging some number that isn't in this interval into the function inverse sine, I'm going to not get anything out of it, because anything outside this interval is not in the domain of inverse sine. All right, you will often also see the inverse sine function written as arc sine. This is slightly more old-fashioned, but is still quite popular in a lot of places. So inverse sine can also be written as arc sine, A-R-C-S-I-N. And so if I want to know what the arc sine of 1 over square root of 2 is, that's the same as inverse sine of 1 over square root of 2. They're the same thing. And so there I want to ask what angle within the interval from negative pi over 2 to pi over 2 gives me a sine value of 1 over square root of 2. And the answer to that question is pi over 4. Actually evaluating these inverse sines follow the same strategy that we used back when we were working on solving equations. So if I want to ask what is inverse sine of, let's say, square root of 3 over 2, Well, the easiest way to do that is to simply write, well, let's let theta equal inverse sine of square root of 3 over 2. And that means that sine of theta is equal to square root of 3 over 2. And theta lies between negative pi over 2 and pi over 2. That's exactly what this equation on the left means. The equation on the left, theta equals inverse sine of square root of 3 over 2, exactly means this statement over here. You can always translate it back and forth that way. From here, you can work it out. So we can work out that the solutions to this equation, well, there are lots of them, but given that we are only interested in the solutions within quadrants 1 and 4, first of all, we note that we're in quadrant 1 because the sine value is positive. And so if we put our theta right there, we've got square root of 3 and 2 as our opposite and adjacent and hypotenuse side lengths. The Pythagorean theorem on both of these will give you a 1 for the adjacent side. And so now we can recognize this as our 1, 2, square root of 3 triangle. And we know that in that triangle, the angle theta has a measure of pi over 3. So that tells us that the inverse sine of square root of 3 over 2 is equal to pi over 3. Now at this point, I should mention a very important warning. We have the following notation. We have that sine squared of theta, for instance, is equal to sine theta squared. We have that sine cubed theta is equal to sine theta cubed, and so forth. And this notation is convenient. It simplifies the expressions and makes things cleaner on the page. However, if we write sine with -1 up above, this is not the same as sine x to the -1. Because this, the left-hand side here, is the angle theta such that sine of theta equals x within quadrants 1 and 4, whereas this side over here is 1 over sine x, or another way of writing that would be cosecant x. The two expressions are not the same at all. So when we use this notation, the shorthand notation with the powers on the sine function, sine, cosine, tangent, etc. functions, then those notations only apply for numbers that are not -1. Now they do apply to all numbers that aren't -1, but the -1 is special and is reserved for the inverse sine function. One reason why some people prefer using the arc sine notation is that it does avoid this confusion. However, the -1 notation is used so ubiquitously that we will be using both of them. So just be careful. Remember that sine to the -1 of x does not mean 1 over sine of x. They just mean totally different things. Okay, so let's talk now about the graph of inverse sine. The easiest way to handle this is to use the facts 6 and 7 from the general theory about inverse functions. That the graph of the inverse function is the reflection of the graph of the original. So let's look at that. Oops, wrong color. All right, so let's look here. Now, we had the following. I'm going to need all these points, 1, -1, and then we'll have pi over 2 here. Pi over 2 is close to 1.5. All right, let me use blue to graph just sine of x. Now, or rather sine of x restricted to the interval -pi over 2 to pi over 2. So the blue here is the function, or is the graph of f of x equals sine x, but with x restricted to -pi over 2 to pi over 2. Now there are a couple of points that I want to mention here. We've got pi over 2 comma 1. We have -pi over 2 comma -1. And I also want to mention the point 0 comma 0. Now the graph of inverse sine x is the reflection across the line y equals x. The line y equals x is the line at an angle of 45 degrees, and I didn't do that super perfectly there, but we will. It's easiest to see what's going on just by working with the points anyway. We're going to approximately be reflecting the blue graph across the green line here. We'll do that in red, and the way that we do that is we take each point on the graph of sine and find the point that we get when we just switch the order of the coordinates. So the point pi over 2 comma 1 is on the graph of sine x. That means that the point 1 comma pi over 2 is on the graph of inverse sine. And that means since 0, 0 is on the graph of sine, that means 0, 0 is on the graph of inverse sine. And because -pi over 2 comma -1 is on the graph of sine, we get that -1 comma pi over 2 is on the graph of inverse sine. So what we get is something that looks like this. So this red line here is the graph of f of x equals inverse sine x. So the graph of inverse sine we see is increasing, just like the graph of sine, but it starts and ends at different places. It comes in and sort of matches up with the graph of sine right near the origin. But that's about it. That's what the graph of inverse sine looks like. We will only occasionally be referring to it, but it's good to have that at hand. All right, let's look at how we can use some of the properties of inverse functions to evaluate some expressions involving the inverse sine function. It turns out that we often wind up composing the inverse trigonometric functions with other trigonometric functions. So, for instance, let's look at the following. Let's ask, what's sine of inverse sine of 1/2? So the let's go through this without thinking about it too hard. Let's just evaluate this from inside to out, and then we'll see that there's a more efficient way of doing it after we get through and evaluate it. So we know that inverse sine of 1/2, if inverse sine of 1/2 equals theta, that's the same thing as saying that sine of theta equals 1/2, and theta is between negative pi over 2 and pi over 2. And we know that if sine of theta is 1/2, and theta is between negative pi over 2 and pi over 2, then that means that theta is pi over 6. That's the only angle that has a sine value of 1/2 within that interval. So that means that sine of inverse sine of 1/2 is sine of pi over 6. All right, so we did that. Now let's look at, well, let's ask what is sine of pi over 6? Sine of pi over 6 is 1/2 via techniques that we've known for very long now. So you'll notice that what happened here is that the sine and the inverse sine sort of annihilated each other. And that's because that's exactly what inverse functions do. If you apply one function and then its inverse or vice versa, you just get back whatever value you plugged into it in the first place. Now, the place where we have to be careful is the fact that the inverse sine function is not the inverse of the full sine function, but that restricted sine function we looked at. So, the facts that we want to use here are the following. Sine of inverse sine of x is equal to x if, now we need to make sure that x is a number that makes sense in here. The domain of inverse sine is only the numbers between -1 and 1. So it doesn't make sense if I plugged a 2 in here for x, then this equation wouldn't hold. But for any number that's between -1 and 1, if I take sine and then negative sine of that number x, I just get x back. The other one that we have to look at is if I take inverse sine of y, that's going to be y, but only if y lies between negative pi over 2 and pi over 2. And the reason for that is that negative pi over 2 to pi over 2 is the domain of the restricted sine function that the inverse sine function is the proper inverse of. All right, so let's look at another example of this. If I take inverse sine of negative 2 pi over 3. Oh, I'm sorry, that doesn't, sorry. I should have chosen something else. 2 pi over 5. So I don't know what sine of negative 2 pi over 5 is. But what I do know is that negative 2 pi over 5 is between negative pi over 2 and pi over 2. Negative 2 pi over 5 is greater than negative pi over 2. And therefore, because I've got the inverse sine and the sine being composed with one another this way, I'll get negative 2 pi over 5. So this is since negative 2 pi over 5 is between negative pi over 2 and pi over 2. What if I switch the order here? What if I take sine of inverse sine of negative 2 pi over 5? Well, this is actually undefined. And this is undefined because negative 2 pi over 5 is less than negative 1. So when we compose the two numbers, or the two functions, we only get back the the input if the input lies in the appropriate interval. So sine of inverse sine of x equals x only if x lies between -1 and 1, only if the number that we plugged in could be the output to a sine in the first place. In this case, -2 pi over 5 simply isn't good enough. An easy way to see why this is, well, first of all, you could just plug this number -2 pi over 5 into a calculator and see that it comes out to something less than -1. But we can also see that by the fact that we know pi is at least 3, which means -2 pi is less than -6. And so -6 divided by 5 will still be less than -1 because 5 is less than 6. So we do have to be careful about our expressions here. Now, we can do something in situations like the second equation when y doesn't lie between -pi over 2 and pi over 2. We aren't necessarily going to get back y itself, but we can do something. We're not totally stuck. So let's look at the following example. Let's look at inverse sine of 3 pi over 4. All right, let's look at the unit circle here. Let's remind ourselves of what sine of 3 pi over 4 is. And this will also help to understand what's going on with this thing afterwards. So we've got the angle 3 pi over 4 here, which means that we have a reference angle to this triangle of pi over 4, because that's the difference between pi and 3 pi over 4. And we know that we can label the sides of a pi over 4 triangle as 1, 1, square root of 2, except we have to apply a negative down here to the side of the triangle that's heading to the left. So we have inverse sine of 3 pi over 4 is going to be inverse sine of, now sine of 3 pi over 4 is going to be 1 over square root of 2, because that's the opposite over the hypotenuse for this triangle. And now we can sort of ignore where all of this came from and just try and evaluate, all right, what is inverse sine of 1 over square root of 2? That's asking what angle within quadrant 1 or 4 has a sine of 1 over square root of 2. So there we can try and graph a triangle. We know that it's going to be in quadrant 1 because this number is positive. If we try to find an angle that makes sine of theta be 1 over square root of 2, that's going to be a positive angle. So we're in quadrant 1, and we can label these sides 1 and square root of 2 for the opposite on hypotenuse, which gives us a 1 down below, which tells us that we're actually looking at an angle of pi over 4. So this gives us pi over 4. Now, you'll notice that we didn't get the same thing. We plugged 3 pi over 4 into this composition of functions. We got pi over 4 out of it, and that's because 3 pi over 4 wasn't in quadrants 1 and 4. It wasn't between negative pi over 2 and pi over 2. However, it is the angle within that interval which has the same sign as the angle that we started with. So this isn't really adding anything new to technically to what we had before, but it is restating it in a useful way for our intuition. So our fact, the inverse sine of an angle is the angle alpha within the interval negative pi over 2 to pi over 2 such that sine of alpha equals sine of theta. If you give me any angle, I can take sine of that angle and get some number out of it. And for that output, there's always going to be some angle within negative pi over 2 to pi over 2, which has that same sine value, or gives the same number when I apply sine to it. Inverse sine tells me what that angle is. It tells me specifically what the angle within the interval negative pi over 2 to pi over 2 is that has that same sine value. So that's one way of interpreting the composition inverse sine of sine. Okay. So we can also try composing these trigonometric functions with other the inverse sine function with other trigonometric functions. So let's try something like that. So what if we asked for inverse sine of cosine of let's do negative pi over 3. Oh, actually, sorry, I wanted 2 pi over 3 for this. Now, we don't have any sort of formulas that allow us to just instantly simplify expressions like this when you've got different trigonometric functions involved. When you've got inverse sine versus cosine, we don't have anything super easy that lets us simplify this real quickly. So we'll just go ahead and work through this directly. So again, on the unit circle, we've got 2 pi over 3, sits in quadrant 2. It's got a reference angle of pi over 3. And so the triangle that we construct here in quadrant 2 has side lengths of 1, 2, and square root of 3, but we associate the negative 1 to the side length on the bottom. So that means that this expression becomes inverse sine of cosine of 2 pi over 3, which is negative 1 over 2. So now we can ignore where everything came from and just ask, what is inverse sine of negative 1 over 2? Well, that means that we're looking for an angle within quadrants 1 and 4 that has a sine value of negative 1/2. Now we know that we're going to be in quadrant 4 because we now have a negative sine value. So sine of negative 1/2 means that our opposite side has length 1 and is pointing in the downward direction, so we label it negative 1. Our hypotenuse has length 2, and that means that our opposite side, or our adjacent side rather, has length square root of 3. And so from here, I can see that this angle has to be pi over 6, but it's pi over 6 clockwise. It's pi over 6 down towards quadrant 4, which means that we have that sine of negative pi over 6 is equal to negative 1/2. And we have that negative pi over 6 is between negative pi over 2 and negative 1/2. And that means that negative pi over 6 is the inverse sine of negative 1/2. So we get negative pi over 6 here. When working with trigonometric functions, or mixed trigonometric functions like this, an inverse sine and a cosine, and the inverse function is on the outside and the ordinary function is on the inside, this is pretty much the only way you have to do it. You pretty much just have to evaluate it from inside out. However, when we compose the other way, there's some simplification that we can do. Let's try to find tangent of inverse sine of -3/5. All right, so here, what I want to do to understand this is I want to go ahead and give this inverse sine function or value a label of theta. Now, I don't know what theta is, and in fact, it's not even one of our standard angles that we work with. But I do know that it has to lie in quadrant 4, because the inverse sine function always gives something in quadrant 1 or quadrant 4, and because we have that sine theta is -3/5, and theta is between -pi/2 and pi/2, that means that theta actually has to be down here in quadrant 4. So perhaps I should specify here that I'm saying let theta equal the inverse sine of -3/5. All right, so once we do that, then we can label the sides of this triangle as -3 on the opposite, 5 on the hypotenuse. The Pythagorean theorem will give us that the adjacent side has length 4. Now, we don't know what theta is, but we don't have to. We're not trying to find theta, we're only trying to find tangent of theta. So once we have this triangle specified, we can now evaluate tangent of theta and see that tangent of theta is just going to be the opposite over the adjacent. So tangent of theta is -3/4, and we can work that out even without having figured out exactly what theta is, without having figured out what inverse sine of -3/5 is. This is a very common technique that we use because it turns out that having a composition of functions where the inside is the inverse trigonometric function shows up surprisingly often in many applications, especially in calculus. Okay, so let's move on to the other inverse trigonometric functions, and we've pretty much talked about all the essential components. Basically, everything that we've mentioned for the inverse sine function applies to the inverse cosine function. The only difference is what interval we have to look at, and where the inverse cosine function gives its results. But all of the strategies and techniques for evaluating it that we've talked about for inverse sine apply to inverse cosine and inverse tangent. So let's look at the graph of cosine to figure out how to make an inverse function for it. So if I graph out cosine, that's not negative, that should just be pi/2. So if I graph out cosine, then I get a curve that looks basically like this. And you can see, just like the graph of sine, this graph does not pass the horizontal line test. It has more than one input for a given output. However, if we ignore everything on the graph to the right of pi and to the left of 0, we do get a curve that is 1-to-1. So cosine x with x between 0 and pi is invertible. and its inverse is what we're going to call inverse cosine. So the definition is as follows. The inverse cosine function, which is denoted as cosine with the upper -1, or arc cosine, is defined by the following statement. Y equals inverse cosine of x if and only if cosine of y equals x for x has to be between -1 and 1, because that's the domain, or that's the range of cosine, and importantly, y is between 0 and pi. So, excuse me, cosine is defined similarly to, or inverse cosine is defined similarly to inverse sine. The only difference is that we're working with cosine instead of sine, and that the angles that are returned by the function inverse cosine always lie in the interval from 0 to pi. Again, intuitively, intuitively, the inverse cosine of an angle of a number x is the angle theta with theta between 0 and pi, such that cosine of theta is equal to x. And we can do all of the same things with the inverse cosine function that we did with the inverse sine function. Let's look at its graph. And let's see, what do I need here? Graph like this. So let's do 1 there, pi is approximately there, pi there, and 1 about there. All right, so the portion of the cosine function that we are inverting is this. So we have a few points on here. We have the point 0, 1. We have the point pi over 2, 0. And we have the point pi, -1. So this is the graph of cosine. The graph of inverse cosine is going to be what we get when we take all the points on the graph of cosine and flip the order of their coordinates. So instead of the point 0, 1 on the graph of cosine, we'll have the point 1, 0 on the graph of inverse cosine. Instead of pi over 2, 0, we'll have the point 0, pi over 2. And instead of the point pi, -1, we'll have the point -1, pi. And so the graph of inverse cosine looks like this. So this is the graph of inverse cosine of x. Again, this is something that we don't use a huge amount, but it does come up sometimes. All right, so the inverse cosine function always gives angles between 0 and pi, or in other words, within quadrants 1 and 2. So we can use that fact in order to write down similar identity or inverse relationships between cosine and inverse cosine as we did for sine and inverse sine. So we have that cosine of inverse cosine of x is equal to x if x is between -1 and 1, and we have that inverse cosine of cosine of x is equal to, or y is equal to y if y is between 0 and pi. And in general, we have that the inverse cosine of y is equal to the angle theta within, let me write it the same way that I did before. Inverse cosine of theta is equal to the angle alpha in the interval from 0 to pi, with cosine of alpha equaling cosine of theta. Excuse me. All right, so other than the difference in the interval where it comes from and the fact that we're using cosine instead of sine, everything works pretty much the same way. Let's look at inverse tangent now. So again, let's remember the graph of tangent. We know that it has asymptotes, which I will denote using yellow. Oops. And we know that the graph of tangent has the following sort of shape. So like that, and then it's got more branches here, more asymptotes here. And as you can see, it, just like sine and cosine, does not pass the horizontal line test. Tangent is not one-to-one. However, we will restrict our domain. Let me make sure and note that these asymptotes occur at -pi/2 and pi/2, and that's in fact precisely the interval we're going to want to take. We're going to basically forget about the tangent, the parts of the tangent function, other than the central branch of it, the copy of it that occurs and goes through the origin. So we're going to say that the inverse tangent function is defined basically by looking at the inverse of this branch that hasn't been marked off. So the inverse tangent function denoted tan inverse or arctan is defined by y equals inverse tangent x if and only if tangent of y equals x and this is for any real number x and y between -pi/2 and pi/2. So this has a similar interval where inverse tan gives results as sine, except of course it doesn't include the numbers -pi/2 or pi/2 because tangent of pi/2 and -pi/2 are undefined. Notice one big difference between inverse tangent and the other functions is that we can actually plug any number into inverse tangent. And that's because the range of tangent is all real numbers, therefore the domain of inverse tangent is also all real numbers. It's actually very interesting to look at the graph of inverse tangent. I mentioned that we aren't really going to use the graphs of inverse sine or cosine very much. It turns out that in applications, the graph of inverse tangent is quite a lot more interesting and a lot more useful. So I'm not going to try and draw both graphs on the same set of axes because that does get a little messy. But on the next slide, I'll go ahead and graph the function inverse tangent. The one thing that I want to mention that's going to help us to get it set up is that the two vertical asymptotes rather, at pi over 2 and negative pi over 2 in this graph of the original tangent function are going to turn into horizontal asymptotes for the inverse tangent function. So the graph of inverse tangent of x looks like the following. We're going to have horizontal asymptotes at pi over 2 and negative pi over 2. And now let's get some points. And the easiest way to get some points on this graph is to look at tangent. Let's look at the original tangent and see what we know about this. We know that tangent of 0 equals 0. And so that means that inverse tangent of 0 equals 0. And that's because the angle 0 is certainly between negative pi over 2 and pi over 2. We know that tangent of pi over 4 is equal to 1. This means that the inverse tangent of 1 is equal to pi over 4. We know that tangent of negative pi over 4 is equal to negative 1. And therefore, inverse tangent of negative 1 is equal to negative pi over 4. So this gives us a few points that we can use to graph out the inverse tangent function. We know the point 0, 0 is on it. We know the point 1 comma pi over 4 is on it, because inverse tangent of 1 is pi over 4. And we know that the point negative 1 comma negative pi over 4 is on it. So the graph of inverse tangent looks like this. Now, what this graph has as an advantage that makes it useful in lots of applications is that it's a very smooth graph. It's got no corners or messy pieces to it. It's actually got a reasonably compact description and definition, and it's defined for all real numbers, but it only goes from negative pi over 2 to pi over 2, and in fact doesn't even reach those two endpoints. It's just bounded above by them. So it's a function that's always increasing, but is bounded at the top and the bottom, and covers all of the, its ranges all the numbers in a particular open interval, all the numbers from negative pi over 2 to pi over 2, not including the endpoints. This type of function winds up being useful for modeling many different kinds of real life and theoretical applications. So the inverse tangent function actually is a lot more interesting than the inverse sine and cosine functions, typically. All right, and then we have the following facts, which are similar to the ones that we had for sine and cosine. If we take tangent of inverse tangent of x, that's equal to x, and that's actually true for all x, and that's because the domain of inverse tangent is everything. And then we have inverse tangent of x is of tangent of y is equal to y for y between negative pi over 2 and pi over 2. And we have that inverse tangent of alpha, or tangent of theta is equal to alpha, where alpha is between negative pi over 2 and pi over 2, and tangent of alpha equals tangent of theta. So we can use these inverse trigonometric functions to handle many situations and solve problems. We're actually going to look at a big application of it in the next section. All right, so let's look at one more example involving inverse tangent. So let's find secant of arc tangent of 7 over 8. As before, the thing that we're going to do is not to figure out exactly what arc tangent of 7/8 is. What we're going to do is we're going to say, let's let theta equal arc tangent of 7/8. This means that tangent of theta is equal to 7/8, and theta is between negative pi over 2 and pi over 2. So let's see what that looks like in terms of a triangle. It's going to be in quadrant 1 because tangent is positive, and we know that theta has to be between negative pi over 2 and pi over 2. So we've got some theta here, and we know tangent of theta is 7/8. So tangent is opposite over adjacent, and so we get 7 and 8 here. This means that the hypotenuse is equal to the square root of 7 squared plus 8 squared, which is the square root of 49 plus 64, which is the square root of 113. So we have that the hypotenuse of this triangle is the square root of 113. And so if we want to know secant of arc tangent of 7/8, that's going to be secant of theta, where theta is arc tangent of 7/8. And now we can read secant off of this triangle. Secant is the reciprocal of cosine. Cosine is adjacent over hypotenuse, so secant is hypotenuse over adjacent. So secant of theta is the square root of 113 over 8. Okay, so let's next talk about how we can use technology and the inverse trig functions to find approximate solutions to problems. So let's do the following. Find all solutions to sine theta equals 0.7 in the interval from 0 to 2 pi. And then round to 3 decimal places. So 0.7 is not a ratio that is in any of the triangles that we're familiar with. If we want to know an angle theta where sine of theta is equal to 0.7, that's not one that we have memorized, and it's not even one that we know. So what we can do is use technology in order to approximate this. So the best thing to do here is to rearrange this equation to write theta is equal to inverse sine of 0.7. Now, it's important to note that this will only give one solution. There are often multiple solutions to a problem like this, and so we'll talk in a second about how to get the other solution. For now, let's look at how we actually evaluate this. So, if you have a scientific calculator, you can come over here, and every scientific calculator will have inverse sine, cosine, and tangent. So you can write, if you're using one like this, inverse sine of 0.7, close parentheses, and you'll see that for us this gives 44.427004. Now, that immediately sets off warning bells in my mind, and that's because I can see my problem is using radians, which means that the numbers that I'm expecting to get out of my inverse trig functions are between negative pi over 2 and pi over 2, which are both of those are less than, it's between negative 2 and 2, it's more restricted than that. So I'm certainly not expecting to get numbers like 44. And I see what I didn't do is I didn't switch into radian mode. So let me go ahead and switch into radian mode, and that looks more reasonable. We get 0.77, etc. So we get theta is approximately equal to 0.77, and because we're not quite at the end of the problem yet, I will use more than 3 decimal places. I'll go ahead and use 5. 775, 39 rounded would be 40. Okay, so theta is approximately 0.7754, and that's going to, as I said, give us one solution. And the reason for that we can see again on the unit circle, and we can see how to get the other one. The inverse sine function only ever gives us angles that are in quadrants 1 and 2. So our theta here is approximately 0.77540. And we know that this point that we've got up here on the unit circle has a y value of 0.7. We don't know what the x value is, but we don't really care too much about that. We're looking for angles with a sine value of 0.7. That means a y value of this point of the corresponding point on the unit circle. There's, of course, another point on the unit circle over here with a y value of 0.7, and it's the point that's reflected across the y-axis here. So if I want to know what this angle is, this other solution to my problem, I'm going to have to figure it out. So for that, we'll go ahead and use the fact that this reference angle we know is going to be 0.77540, or theta, which means that the actual angle we're interested in will be pi minus theta. And so that'll give us the other solution. So the theta that we started with here is one solution, pi minus theta is the other solution. So for us, that will be, we can take pi, let's clear it all out. We can take pi minus 0.77540 to get that this is approximately 2.36619. And here is the other solution for us. So our answer here will be rounded to 3 decimal places, 0.775 and 2.366. Those are the two angles in the interval from 0 to 2 pi that have a sine of 0.7. And that's how we can use the inverse trig functions to work these out. Now, getting all of your solutions to equations like this requires you to do some manipulation here. But there are some patterns that we can work on that will help you out here. So they are different for sine and cosine and tangent, but that's all right. We can work it out. So solutions to our basic trigonometric functions, or trigonometric equations. So if we have trigonometric equations, I should say these are within the interval from negative pi to pi. So it's one complete revolution around the circle, but rather than going from 0 to 2 pi, it's from negative pi to pi, and furthermore, we've got from negative pi to pi, not including negative pi. And because the inverse trig functions give negative values, we'll sometimes be getting our values within negative pi to pi. So sine theta equals x has solutions as we saw before. Theta equals inverse sine of x and pi minus inverse sine of x. Those two numbers, inverse sine of x and pi minus inverse sine of x, are always going to be our two solutions to the equation within the interval from negative pi to pi, just as we saw last time. Now, cosine of theta equals x has solutions. Theta equals inverse cosine x, of course, and then theta equals negative inverse cosine x. Now, what's going on here with the cosines is that if I take the inverse cosine of some angle or of some number, and I get some angle off here, sorry about that, then if I take the negative of that angle, if I've got theta up above and then negative theta down here, these two have the same cosine value, because these 2 points have the same x value. So if inverse cosine of x is one of our solutions, then negative inverse cosine of x is another one of our solutions. And then tan theta equals x has solutions. Theta equals inverse tangent of x, and then inverse tangent of x plus or minus pi. Here we've got to be a little bit flexible. If you add or subtract pi to your inverse tangent, then you'll get another solution to the equation, and then whether you add or subtract pi in order to get something within the interval from negative pi to pi just depends on whether the original inverse tangent was positive or negative. Of course, once you have solutions within the interval from negative pi to pi, you can find lots of other solutions within other intervals as well. So let's see how we can do this. Let's apply that here. So let's find all solutions to the equation cosine of theta is equal to negative 1/3 within the interval from 0 to 2 pi. And we'll go ahead and use the facts that we have up here. So we know that theta equals inverse cosine of negative 1/3 is going to give us an angle theta, which will be a solution to this equation. So if we come down here and we write inverse cosine of negative 1, pardon me, inverse cosine of negative 1/3 that's going to give us 1.91. I'll just use a couple of decimal places here for illustration. So that's going to be one of our solutions, but then we also have the solution theta equals negative inverse cosine of negative 1/3, which will be negative 1.91. And that's going to give us two solutions within a single cycle of the circle, but these aren't the solutions within the interval from 0 to 2 pi. So to find more, we can, of course, add any multiples of 2 pi that we like. We can always add 2 pi over and over and over again. Now, we don't need to in the first case. This 1.91 is fine. That's sitting over here in quadrant 2. But our negative 1.91 solution, that's sitting in quadrant 3, but it's getting there using a negative angle. If we can add 2 pi to that, then that'll work. Then that'll give us a coterminal angle within the interval 0 to 2 pi. So we'll take theta equals negative 1.91 plus 2 pi, which equals, so coming back over, if we take negative cosine, negative 1/3, which was negative 1.91, and we add 2 pi, then we get 4.37. And that's going to be our other solution within the interval from 0 to 2 pi. So our answers are going to be 1.91 and 4.37. All right. We can use these facts right here in order to even solve equations that we didn't have a good way of doing before. So let me just get one started. Let's say we want to solve the equation 3 cosine squared theta minus 2 cosine theta minus 1 equals 0. Now, pardon me. Sorry. 3 cosine squared minus 3 cosine theta minus 1 is what I wanted to do for illustration purposes. Now, one thing that we can do here is we can use the quadratic formula. And we can get, using cosine theta as the variable, and we can get that cosine of theta is equal to negative b plus or minus the square root of b squared minus 4 times a times c all over 2 times a. And you get cosine theta is equal to, and we'll get 3 plus or minus the square root of, let's see, that'll be 9 plus 12 is 21. So we get cosine of theta is equal to 3 plus or minus the square root of 21 over 6. So that means that cosine of theta is equal to 3 plus the square root of 21 over 6, or cosine of theta equals 3 minus the square root of 21 over 6. So from here we can get that theta is equal to inverse cosine of 3 plus the square root of 21 over 6, or theta equals a negative inverse cosine of 3 plus the square root of 21 over 6, because those are the two solutions that we get from the previous page. And from here we can get that theta is equal to inverse cosine of 3 minus the square root of 21 over 6, and theta equals negative inverse cosine 3 minus the square root of 21 over 6. But then of course we still aren't quite done, because we can plug these into the calculator, get numbers out of it, and those will give us solutions all within the one cycle around the circle from negative pi to pi, but then we need to add 2 pi n to get all the solutions. So in this case, we're going to get 4 infinite families of solutions to this equation, assuming that all of these numbers, 3 plus square root of 21 over 6, 3 minus square root of 21 over 6, are all between -1 and 1. Frankly, I'm a little suspect of this 3 plus square root of 21 over 6 here. Oh, and I just realized that I was blocking that part of the page with my calculator. Sorry about that. Let me pull that up here. Looking at this, if I do 3 plus the square root of 21 over 6, notice that this right here is approximately 1.26. In particular, it's greater than 1. That means that inverse cosine of this number is not defined. So we actually get no solutions out of these two equations here, or these two solution sets here. Let's check 3 minus. If we turn this into 3 minus square root of 21 over 6, yes, that does work. That is a number between -1 and 1, and so we can go and do inverse cosine of that angle. So what we'll get out of this is that inverse cosine of 3 minus the square root of 21 over 6 is 1.838, rounding to 3 decimal places. And then this down here will be -1.838. And so our final answer to this question will be two infinite families of solutions. I'll go ahead and put them over here. I'll erase the one that didn't work. And so we get that our answer is 1.838 plus 2 pi n and negative 1.838 plus 2 pi n for n an integer. All right, the last topic, and I know this has been a long video, the last thing I want to mention is that we can simplify some compositions of trigonometric functions and inverse trigonometric functions that have variables in them. And this is something that is quite useful in many applications. So, for example, let's find the sine of inverse tangent of x. Now, of course, we're not going to get a number out of this because x is a variable. It could have lots of different values. But it turns out that we can simplify this and express it as an algebraic expression, purely algebraic, without using trigonometric functions. And let's see how to do that. We're actually going to do that similarly to how we did it before with simplifying expressions like this. We can let theta equal inverse tangent of x. Then that means that tangent of theta is equal to x, and theta is between negative pi over 2 and pi over 2. It turns out that it turns out that it's good enough to look at triangles. We can construct a triangle with this angle theta and label its sides. Only this time we aren't going to label the sides using just numbers, but also algebraic expressions. Now, we need to label the opposite and adjacent sides of this triangle in such a way that tangent of the triangle is x. The easiest way to do that when you don't actually have a fraction as the output of your trigonometric function is just to put it over 1. So we can label the opposite and adjacent sides of this triangle as x and 1. And this gives us a triangle with an angle theta here whose tangent is x over 1. Now, by the quadratic formula, we can figure out that the hypotenuse of this triangle has length square root of x squared plus 1. And therefore, we can actually write down what sine of this is. So this means that sine of inverse tangent of x is equal to sine of theta, and sine of theta we can read off of this triangle. It's x over the square root of x squared plus 1. So when you're composing two trig functions in this way, an ordinary trig function on the outside and an inverse trig function on the inside, and the trig function on the inside has a variable as its input, or an algebraic expression as its input, you can always simplify it to be an algebraic expression. So instead of writing sine of inverse tangent of x, it turns out that's just another way of writing x over the square root of x squared plus 1. And this type of translation allows us to turn trigonometric types of problems into algebraic types of problems, which, depending on the situation, can be very helpful.